At this point, we've learned how to take a second-order system and put it into that standard format of transfer function is equal to a times omega n squared over s squared plus 2 zeta omega n s plus omega n squared. Now, that value, zeta, and you can see the difference between the zeta that I've drawn and this fancy-looking zeta over here, but I will write zeta, so we know that my less pretty zeta and this nice typed-up zeta are the same thing. When we look at the different values of zeta, as they go from 0 to 1 and higher, we have different responses to a step response. So if we have a step function input, where we go from 0 to a value of a system, we can see different responses based off of what our zeta value is. So in our zeta value, if we have that zeta is equal to 0, that would be that our poles, and let's add in a little column for poles, or there is a column for poles, but we can say that those are equal to plus or minus j omega n. And we're going to use j for our imaginary numbers because you could either use j or I, either one is fine. For now, for this sheet of paper, we're using j. So we have s is equal to plus or minus, and we only have imaginary components. And what we have here is we have a real and imaginary plane. So we can say that this is our real axis, here is our imaginary axis, and we're going to plot any of our imaginary components in the vertical and any of our real components in the horizontal plane. So this is an undamped system. We have a system that will oscillate forever. It is neutrally stable, to use something from earlier in this lesson, and it will oscillate forever if we provide a step response. And here, this next system, we're going to look at functions where zeta is between 0 and 1. If it's between 0 and 1, we call it an underdamped system. This is a system that will oscillate for a little bit, but those oscillations will pare down over time. So we have that if zeta is between 0 and 1, that means that s is going to be equal to negative zeta omega n. S is equal to negative zeta omega n on the real axis, and plus or minus j times omega d. I'm just going to write omega d for now, and omega d is called our damped frequency, and that is equal to omega n times 1 minus zeta squared. So all of these are just solutions you get if you take the characteristic equation, solve for s with the provided zeta values. So in this session, we have an underdamped system, which means that if we add a step function, the system will oscillate a little bit and then eventually reach the equilibrium without any oscillations. So if you think of putting something on a typical scale, you might see the reading on the scale oscillate back and forth, but then it stops after a small amount of time. Okay, next page. Now, if we have zeta is equal to 1, then we can say that we have poles are both at negative zeta omega n, but they are repeat poles. And repeat poles occur, zeta is equal to 1, and this is called a critically damped system. So critically damped system looks a little bit like a first order function, but it has its interesting properties. We actually don't deal with them too much in this class because they're less frequent, but this comes from solving it when we have two repeat poles, and we see that there's no oscillation, and we eventually reach our steady state value, and it will occur a little bit faster than an overdamped system of the same natural frequency. So overdamped is when our damping ratio is greater than 1. So if it's equal to 1, it's damped. If it's less than 1, it's underdamped. If it is 0, it is undamped. But if it's greater than 1, it is an overdamped system. And we have two poles, at negative zeta omega n plus omega n times zeta squared minus 1. And for this, we can plot the poles where we have two real poles, because if zeta is greater than 1, then the square root of zeta squared minus 1 is going to be a positive number, so we don't have that j term. And we then have an overdamped system. An overdamped system is going to act a lot like a first order function. We're going to get to that later in this lecture. So here we have the four scenarios of our systems. So we had zeta is equal to 0, zeta is between 0 and 1, which is underdamped. We have zeta is equal to 1, critically damped, and zeta is greater than 1, which is overdamped. So we now have different scenarios based off of that zeta function. And if we want to go one step further and look at impulse functions, here we have some scenarios where we start off with different versions. So if we have zeta is greater than 1, where we have a pole in the right-hand plane, these are all overdamped systems that are unstable. Because every time we have any poles in the right-hand plane, that tells us that the real component is greater than 0, which will cause the system to be unstable. If we have unstable and a zeta that is between 0 and 1 for an unstable system, or we could say that it's between negative 0 and negative 1, that's going to be an unstable system which will oscillate back and forth while approaching infinity. We can also have neutrally stable systems, which either have oscillation, where the greater your omega n is, greater that natural frequency is, the higher the frequency that the system will oscillate at. And if there's no natural frequency, we just have a neutrally stable system that moves over. Now, if we had a overdamped system that has only real components, if it is closer to the right-hand plane, it's going to have a slower reaction than one that is further from the right-hand plane. And if we have that it's an undamped system, let's use one more color, then that's going to be a system that will oscillate and then eventually go back to its equilibrium. So all of these, you'll notice, are reactions to impulse as opposed to step functions. You should have that written on your paper. It just didn't fit in the screenshot I took.